So, we will do a few more problems related to CD nozzle. So, the question 1, I have a CD nozzle. I have two sections, section 1 and section 2. My A1 is 25 centimeter square, A2 is also 25 centimeter square. P1 is 120 kilopascal and my stagnation temperature is 300 degrees Celsius. P0 is 171 kilopascal. Find m dot area at the throat m2. M dot area at the throat and m2. Assume isentropic flow. Okay. So, the moment you know it is isentropic flow, you know three things: T1, P01 equals T02, P01 equals P02 and A1 star equals A2 star. So, these three things are implied when you say isentropic flow. We will use this information to do the problem. So, first we have P1 by P01, which is 120, it is 120, it is 120 by 171, which is 0.7. The Mach number at 1 is then, so I look at the tables, gamma 1.4, P1 by P0 is 0.7, 0.7 is Mach number 0.73, 73, which has a A1 by A1 star, which is at m equals 0.73. So, I look at the tables, m equals 0.73, my A by A star is given as 1.074. But my A1 equals A2 and we also know A1 star equals A2 star. Okay. So, my A2 by A2 star is also my A1 by A1 star, which is now 1.074. So, this A by A star has two Mach numbers. So, one is already here 1.74, the other Mach number is, so you look at the supersonic solution of this area ratio 1.0 1.074. 1.074 will give me a Mach number of 1.32. Okay. So, my M2, so the fluid that comes here M1 0.73 reaches a Mach number of 1.32 for this area ratio. Okay. So, somewhere it is crossing 1, which is happens at the location where dA is 0, which is your throat. So, your A star is your A throat. Okay. So, your throat value, A throat is your A star is A2 into 1.074, A2 is 25 centimeter square, which is A2 by point. So, 25 by 1.074, it will be around 25. So, it is 24, 23.3 centimeter square. So, that would be my throat area, okay, given this condition. I also need to find my m dot. So, m dot is now the m at Mach number at throat is 1, okay, implying flow is choked or the nozzle is choked. Okay. So, if it is choked, the maximum flow rate A by A star into root of T0 by P0 is a constant, which again is given here in the gas tables. Which is gamma by R square root into 2 by gamma plus 1 to the power gamma plus 1 by gamma minus 1 into 1 by 2. Okay. So, your m dot you can find it. A star is known, A star is 23.3 into 10 power minus 4, root of T0 is known 300 plus 273 divided by P0 is known 171 into 10 power 3 equals this particular constant. Okay. So, you can find your m dot in kg per second. Okay. So, this is all because the flow is assumed to be isentropic. So, somewhere here between station 1 and 2 the flow is isentropic. So, somewhere across the Mach number reaches 1, which happens at the throat, which since it is Mach number equals 1, the A star is your A throat. So, we have computed our A throat and then obtained this particular relation. Okay. So, if your A2 is not same as your A1, then you cannot write this, but you can still find your A2. So, if you are given A2, you can still find the ratio and obtain your M2 just that it might not be the same ratio as this, it would be some other solution which has to be a supersonic solution, because we have said this would be at m equals 1. Okay. Fine. So, now we go to the next question. Again a CD nozzle at some section 1, my V1 is 200 meters per second, T1 is 300 Kelvin, P1 is 125 kilopascal, M exit is greater than 1. Find m dot A1, okay, if the throat area is 35 centimeter square. Okay. So, the CD nozzle flow is coming in at section 1, we have the value static values, the exit Mach number is greater than 1, implies exit is greater than 1, flow is chocked, the nozzle is chocked, okay, implies your A throat is same as your A star, which is same as 35 centimeter square. So, at station 1, my M1 is V1 by A1, which is V1 by gamma or T1. So, V1 is 200 root of 1.4 into 287 into T1 is 300. So, this gives me a Mach number 0.58. So, for this Mach number, assuming flow to be isentropic, A star is constant. So, if my A star is constant, my A1 by A star at Mach number 0.58, I look at the tables, Mach number 0.58, has an A by A star of 1.213. So, my A1 is 1.213 into A star, which is 35 centimeter square. Okay. Now, you need to find m dot. So, m dot, since m at the throat is 1 or the m at the exit is greater than 1, your m at throat is 1 and the flow is chocked, use this relation find your m dot. But what about T0? You have T1 by T0 at m equals 0.58, P1 by P0 at m equals 0.58. Okay. From this you can find your T0 and P0, substitute that here, A star is already known, so you can find your m dot. Okay, you can also find it from the throat value or from the inlet value, or m dot is rho 1 A1 V1, rho 1 is P1 by R T1 into A1 into V1. So, A1 now we have found, V1 is given, P1 and T1 is given. This again. Okay. So, you can check whether this is same as that. So, this is under the assumption flow is choked. No. Yeah, this is under the assumption flow is choked. Okay. Otherwise, you use, since the Mach number at station 1 is known, that also can be used. So, m dot by A1, okay, into T0 by P0. Then you have a relation for m1 1 plus gamma minus 1 by 2 m1 square gamma plus 1 by 2 gamma minus 1. Thanks. Correct. Minus of gamma plus 1. Okay. So, your A1 is known, M1 is known, you can find your m dot. Okay. So, now we will do a different problem. So, I have two nozzles, two CD nozzles, each of them has two different throat area, and there is something that is connected here, which is the typical case of a supersonic wind tunnel. So, there is some shock or some non-isentropic process that is here. So, the process is non-isentropic, but no heat transfer, no shaft work, okay. And this is supplied from a tank kept at T0 and P0, okay. So, I have A1 A throat 1 and A throat 2. So, my temperature here is 300 Kelvin, temperature here is some 200 kilopascal. Okay. So, what is the stagnation pressure loss? Okay. AT1 by AT2 is given as 2. So, what is the stagnation pressure loss? So, if it is an isentropic process, we know T01 equals T02 or T0 stagnation temperature is constant and stagnation pressure constant and our A star constant, but here it is non-isentropic. Since there is no Q and no shaft work, you can still write this, but P02 by P01 depends on your entropy change. Okay. So, this is your drop in your stagnation pressure. Okay. So, this is a non-isentropic process. We also know this. A1 star. Okay. So, we will use this relation. Now, since the flow is non-isentropic, we will use this relation to find our drop in pressure. Okay. So, your throat area, assuming the throat area is chalked, A2 star is your A throat 2, A1 star is your A throat 1. So, I can find my P02 to be P01 into AT1 by AT2. So, my AT2 by AT1 is 2, because your second throat should be larger than your first throat. Okay. So, the process is you have you are generating a supersonic flow, and at the exit you have a supersonic flow. That supersonic flow remain constant in your constant area duct, and then it is reduced by a supersonic diffuser. So, this would act as a diffuser and it would eject into the atmosphere slowly. So, there are no back pressures from the nozzle. Okay. So, your second throat would be larger. Okay. So, this ratio is AT2 by AT1 is 2. So, which is P01 is 200 kilopascal by 2. So, this would be 100 kilopascal. So, this is your reduction in your stagnation pressure. So, there is some loss of your stagnation pressure along the non-isentropic process. We are going to do the shock analysis, and you will see that this has some implication in the flow. So, your strength is stagnation pressure is your strength of the or the power at which you have the flow. So, this is a measure of the strength of the flow, and that is lost due to your non-isentropic process. Okay. So, it is coming at full steam with P01, then suddenly it encounters a non-isentropic process and loses all the steam. That is what it typically means. So, we will discuss that in the next week. Okay. And the examples on over expansion and under expansion, we will take it up when we discuss shocks and oblique shocks. So, we will come back to these examples again at a later stage to do some more problems involving shocks and expansion waves. The diffuser part or supersonic diffuser also we will come back and take it up after discussion on shocks and oblique waves, okay, because supersonic diffuser is also an important part. So, we will take it up that as well as at a later point of time. Okay, thank you.